Hi, in this presentation I'm going to give a brief summary of my final project. For my final project, I built a recommender system on Apache Spark for a data set with over 1 million ratings. The data set that I worked with was the Movie Lens 1 million data set, which includes 1 million ratings from approximately 6,000 users and 4,000 movies. The ratings are all whole numbers from 1 to 5 stars, and each user in the data set has at least 20 ratings. The approach that I used was to use some of the matrix factorization techniques in the MLlib library on Apache Spark. In particular, I used the alternating least squares algorithm. I tried optimization of the algorithm parameters, and then I also tried using the baseline predictor in terms of user and item biases, and then tried modeling the user-item interaction term separately. In terms of evaluation for all the models, I tried to use a consistent evaluation scheme, which included training and test random split 80-20 of the ratings data set, and then evaluating model performance in terms of the root mean squared error of the model predictions on the test set. In terms of the work setup, I accessed Apache Spark using Databricks and used the R and sparklyr package within a Databricks notebook. So after installing all the required packages, I started out by preparing the data. I had already downloaded the Movie Lens dataset into my GitHub repo, so from Databricks, I just read in the data from my GitHub repo. What we can see is that the full ratings matrix included over 1 million ratings from over 6,000 viewers and close to 4,000 movies. The ratings matrix was almost 96% sparse out of a total of close to 24 million viewer movie pairs. So after loading the data, I did some exploratory data analysis, loaded the data into a Spark table, and then started taking a look at the distributions of the data. And in particular, I looked at the histograms of ratings and rating counts and average ratings, both per user and per movie. First of all, the overall mean rating of the data set was about 3.5, actually close to 3.6. I started out by looking at rating counts and average ratings per user. The ratings per viewer ranged from 20 at the low end to, at the high end, over 2,300. The mean number of ratings per viewer was 166, median of close to 100. The average rating per viewer was about 3.7, which indicated that most people tend to give above average ratings to movies. So here's a plot of the rating counts per user and the average ratings per user, where again we see the mode or the peak of the distribution just under 4. I also looked at rating counts and average ratings by movie, and you know what you could see was that the number of ratings per movie ranged from 1 to over 3,400. The average number of ratings was 270 with a mean of 124. So distribution of rating counts per movie, and then average ratings per movie, where again the mode or the peak of the distribution is about 3.5, close to 4. I also looked at the most frequently rated movies, in other words, the movies that had the most number of ratings. The top 3 most frequently rated movies included Hairspray, A Little Princess, and Goodfellas, although those had close to 3,000 or over 3,000 ratings. The most highly rated movies, in other words, the movies that were most highly rated by viewers, the initial list was skewed by movies that were rated by fewer than 10 users. So after filtering out and only looking at movies with at least 50 ratings, the top 3 most highly rated movies included Crimes and Misdemeanors, Peter Pan, and Suture. All of those were rated above 4.5 stars. So I then started developing different models. The first model was a simple model, just the baseline predictor based on the overall mean rating, the user bias and the item bias. I won't spend too much time going through the details since we had a project already on the baseline predictor, but briefly, I partitioned the data into training and test splits in an 80-20 random split, trained the model on the training set, predicted ratings for the test set, and then evaluated the model performance in terms of accuracy of predicted ratings using the root mean squared error metric. The upshot in terms of evaluation results was that the model number one, the baseline predictor, had a root mean squared error of just under 1 whole rating star, about 0.9. The second model I looked at was a pure alternating least squares matrix factorization model, where I used the ML-ALS function in SparklyR, used the same evaluation scheme as above in model number one. So in other words, 80-20 random split of the training and test set. Trained the model on the training set, tested accuracy of ratings on the test set. So one thing to point out in terms of the ML-ALS function in SparklyR was that I used the default values for all function parameters, and in particular the rank of the matrix factorization default value was 10, and the regularization parameter default value is 0.1. As we'll see below, we vary those values to see if there's any difference in model performance. One other thing worth mentioning was that the cold start strategy parameter, I had to set that to drop. What that does is it basically instructs the model during prediction to ignore any users or items that were not included in the training set. Otherwise, the model would predict NA, and the NAs will end up causing problems for the root mean squared error prediction number. So with that, I'll just move to the evaluation. One thing to point out is when computing the root mean squared error, I just wanted to ensure that the predicted ratings were between 1 and 5 stars, so I imposed upper and lower bounds of 1 and 5 stars to guarantee that. And the final numbers in terms of the root mean squared error were model number 2, the pure ALS model, had a root mean squared error improvement. There was a gain versus the baseline, and the final root mean squared error was 0.82 for the training set, 0.87 for the test set. The third model I looked at was ALS with the baseline model, where essentially, similar to one of the readings that we had earlier in the course, I looked at setting up the predicted ratings as the sum of the baseline predictor and then a user item interaction. The baseline predictor we computed above, the baseline, but the user item interaction is what I used the ALS matrix factorization to model up. So, effectively the way to interpret this is that the user item interaction represents the remaining effect between the users and movies after accounting for the overall rating and the bias of individual viewers and movies. So in terms of model development, again, I followed the same basic scheme as above, training test split, 80-20. I used the baseline predictor from model number 1, and then in order to model the user item interaction, I had to subtract out the baseline predictor from the ratings and then modeled that using the ML-ALS function. But then for computing the overall predicted rating, I had to add back the baseline predictor in order to compute the root mean squared error. So again, I'm not going to go through all the details, but in terms of evaluating the model and computing the root mean squared error, I'll just point out in the root mean squared error function, I had to add back the baseline predictor to the user item interaction to get the overall rating. And then again, as before, I imposed upper and lower bounds to ensure that the predicted ratings were between 1 and 5. And finally, for model number 3, the model performance was 0.82 and 0.874 for the training and test sets. So very, very close to model number 2, slightly worse, but hardly noticeable between number 2 and number 3. In the fourth model, I returned to model number 2, which was the best performing model, and I wanted to see if there was a way to improve performance by varying or tuning the hyperparameters of the ALS factorization algorithm. And specifically, I varied the rank as well as the regularization parameter to see if we could improve the root mean squared error. For rank, I varied the values of the rank from 5 to 100, where the default value is 10. And regularization parameter, I varied that between 0.01 and 0.1, where the default value is 0.1. So in all, I looked at 10, in other words, 5 times 2 iterations. And to do that, it took roughly 10 minutes on Apache Spark from the Databricks platform. So in order to accomplish that, I had to I followed code that was in the SparklyR documentation for the ML tuning function using machine learning pipelines and creating a hyperparameter grid. The results were interesting in that what it showed was that basically the default values of 0.1 for the regularization parameter and 10 for the rank ended up producing a root mean squared error that was about as close as the optimal values. The optimal values, at least for the ones that I considered, were 0.1 for the regularization parameter and 100 for the rank, but the gain in RMSE was very slight. It was 0.867 versus 0.87. So again, hardly noticeable, and I'm not sure that it's really worth the additional computational expense. So finally, in terms of conclusions, the main findings were that out of the 3 models I considered, model number 2 performed the best, which was the pure alternating least squares model that had the highest accuracy or lowest error metric on the test set. When hyperparameter tuning in model number 4, the best result was achieved by a regularization parameter of 0.1 and a rank of 100, but the root mean squared error gain was very slight compared to the default values. So finally, just a few observations. I found that working with the MLlib package in Apache Spark, it looks like there are a lot of powerful tools and techniques, and I'd love to spend more time to become more familiar with that. I also found working in the Databricks platform generally pretty convenient and hassle-free, although occasionally, most likely when I was overwhelming the cluster, processes would get terminated without any warning. In terms of the SparklyR package, I found that it provided a nice interface to the MLlib features, but it seemed that it wasn't an inclusive package. In other words, it didn't include all of the MLlib features. From my project proposal, I initially had wanted to look at singular value decomposition as another technique, but apparently SparklyR doesn't include SVD decomposition of ratings for a ratings matrix in the package. I also found from the last project, Project 5, that using SparklyR within RStudio wasn't very stable, and I was never able to get the ML ALS function working. And I don't know if that was a bug in the SparklyR package or if it was just an artifact of a setup on my home PC. Finally, I'll just note that if I had more time, I'd love to spend some time looking at hyperparameter tuning in more detail. There were some interesting trends in terms of the trade-offs of regularization parameter versus rank, and it'd be interesting to see if you could achieve any meaningful material improvement and at what cost in terms of additional computational time and expense. So that's it for my final project. Thank you very much.